If you're optimizing without reframing the constraint, you're just polishing drag. Welcome back to AI on AI. Today we're digging into agentic coding systems that write expert-level scientific software using LLMs plus search. You know, the whole code, run, score, improve loop.
Right? We're talking scorable scientific tasks, where a program gets a number and the agent climbs that hill until it finds a better one.
The trick is pairing an LLM rewriter with tree search, PUCT-style selection, rank-based scoring, and a sandbox that, keeps the explosions contained.
From a business lens, it's time to incite arbitrage. Compress months of trial and error into days, and you can pull ahead on strategy, not just horsepower.
In biology, it combined linear correction with graph-building neighbors to tackle batch effects, essentially stitching datasets while preserving cell-type signal.
Public health forecasting saw hybrids beat long-standing ensembles in rolling windows, mixing simple climatology with autoregression and even counterfactual simulations for variant shocks.
Remote sensing segmentation, classic UNet++, and a transformer variant with heavy test time augmentation, like giving the model multiple camera angles before it decides.
Neuroscience had a curveball. A time series model outpaced a beefy video predictor at longer horizons, and a biophysical-flavored variant stayed competitive with far less compute.
It's like we used to debug spaghetti code in the dark. Now we've got a searchlight and, honestly, a decent map.
Concretely, the agent samples code variants, executes, ranks results, and the PUCT term nudges exploration. Randomness comes from model sampling, not dice roll rollouts.
And you can inject research ideas, summaries, pseudo-steps, and even recombine two methods. Embeddings showed clusters of distinct solution families emerging.
Strategically, treating literature as Lego bricks means the pipeline learns to refactor, not just tune knobs, faster tech transfer into production.
Pushback? Are we just gaming metrics? Overfitting to leaderboards is a real risk when the score is the North Star.
We anticipated that. Separate datasets for hill climbing, held-out metrics, and ablations that showed the linear plus neighbor combo mattered beyond hyperparameters.
Contrarian take. The winners often anchored on boring baselines, climatology and AR then layered complexity, stability first, fireworks second.
So ensembles are just models wearing trench coats, standing on each other's shoulders to buy a ticket to the leaderboard.
Surprise for me, a scratch-built forecasting library using basic tooling rivaled foundation models by decomposing level trend seasonality and correcting residuals.
You see it in breakthrough plots, green dots where the score jumps after a small code edit. The pit crew tweaks the car mid-race.
Even numerical integration improved via series acceleration with safe fallbacks, acting as a drop-in when standard routines stumble.
Enterprises need artifact tracking, prompts, diffs, scores, plus reproducibility guarantees before this becomes standard in regulated domains.
Recent moves in agent frameworks and transparency proposals are nudging toward audit logs, deterministic replays, and safer execution contracts.
In bio, guardrails meant no label leakage, using metrics like ASW, LISI, and PCR, scaling to millions of cells without, melting GPUs.
Cost-wise, several solutions trained on modest hardware in hours. That matters for carbon budgets and burst capacity planning.
Risks, hallucinated code, unsafe ops licensing. How are you containing that blast radius?
Sandboxing resource caps, an allow list of libraries, and secured I/O, plus runtime checks to kill long tails and bad syscalls.
Provenance helps. We attach idea snippets, code diffs, and score deltas. What gets measured gets improved, becomes traceable.
Add unit tests, data invariants, and simulation checks. Measure twice, cut once, then let the agent iterate.
Operationally, set SLAs around accuracy uplift and retraining cadence, with human checkpoints where risk concentrates.
Slight pushback, Humans can bottleneck, triage by uncertainty and novelty, so reviewers only see spiky cases.
Building on that, route high variance batches to manual review in lab pipelines. Low variance runs auto-ship.
Open versus proprietary. Where's the advantage?
Open components thrive when tasks are scoreable. Private edge shifts to data, feedback loops, and domain-specific evaluation harnesses.
Heuristic time, good input, good output. The best breakthroughs came from crisp method summaries and high-quality idea recombinations.
Embeddings showed diverse clusters, linear, nonlinear, deep, so diversity in prompts and seeds helps escape local optima.
Search is a metal detector. You still need to sweep the field methodically or you'll miss the gold 2 feet away.
Don't just price peak score, price exploration speed. Fail fast, learn faster is the ROI driver here.
In the wild, weekly epidemiological forecasts used rolling validation and change point detection to adapt to drift.
In biology, atlas-scale integrations enable downstream discoveries, cross-lab analyses that were painful before.
For geospatial ops, disaster mapping and land use, test time augmentation tempered seasonal shifts and weird lighting.
So TTA is basically models getting second opinions before signing the report. I respect the caution.
Next up, agents composing agents, hierarchical searches, multi-objective fitness for robustness, speed, fairness.
I want benchmarks that fix energy and latency budgets alongside accuracy, success under constraints, not just best score.
Prediction: every research team gets an AI co-developer tuned to its scoreable tasks, wired into governance and observability.
That's our show. Measure, search, and iterate. The future looks like a lab bench with a turbo button. Stay with us for a concise summary of the highlights.
Narrated by the AI voice of Shri. The central theme is an artificial intelligence system that writes and improves scientific software to maximize a measurable quality score. The question is whether automated code search can reach or exceed expert performance across many scientific tasks. The approach pairs a large language model with tree search to rewrite code and climb a scoring metric. Tree search is a method that explores many candidate solutions while balancing trying known good ideas and testing new ones. The system also injects research ideas from papers, textbooks, and search tools into the prompts that guide code generation. Empirical software means code designed to optimize a specific, objective quality score on real data. A scoreable task is any problem where solutions can be automatically judged by a clear metric. On single-cell RNA sequencing batch integration, the system often beat published methods on a public benchmark. A standout solution combined a linear correction method called combat with batch, balanced nearest neighbors to improve integration quality. Batch effects are unwanted technical differences between datasets that can mask true biological signals. The method also programmatically recombined ideas from multiple papers, with many hybrids outperforming their parents. The system discovered 40 new single-cell analysis methods that surpassed top human results on the leaderboard. In epidemiology, it generated 14 forecasting models that beat the Centers for Disease Control and Prevention ensemble. Forecast accuracy was measured using weighted interval score, which rewards precise predictions and well-calibrated uncertainty. Hybrid models that fuse simple climatology with autoregressive or machine learning components were especially strong. New strategies use Monte Carlo scenario simulation and change point detection to adapt when disease dynamics shift. In geospatial segmentation, the system built models that exceeded reported results with mean intersection over union above 0.8. Test time augmentation means predicting on several transformed versions of an image and averaging the results for robustness. In zebrafish brain activity prediction, time series models outperform the best video model for most future steps. These models trained much faster and exploited cross-neuron information using shared context and learned embeddings. A specialized one-step model added attention and feature modulation to improve immediate predictions. On general time series forecasting, per dataset searches beat many foundation models on a public leaderboard. A unified library built from basic components matched strong baselines using adaptive configurations and mean absolute scaled error. In numerical integration, the evolved code partitioned infinite domains and applied Euler transformation to accelerate slow series. It solved 17 of 19 difficult integrals where a standard library failed, while retaining drop-in behavior when easy. Experts note that not all generated codes are perfect, and some fail on memory or edge cases. The system mitigates overfitting by using holdout datasets and validation windows, yet real-world deployment still needs caution. Open questions include interpretability, reproducibility, and how to guide automated search toward principled scientific insight. Future directions include incorporating biophysical structure into neuroscience models and expanding literature-aware idea generation. If validated and used responsibly, this workflow could speed up scientific discovery wherever results can be scored automatically. Tag a peer who challenges your thinking and swap your top 2 takeaways from this discussion.